Now the next trend we'll look at is ionization energy, which is the amount of energy it takes to remove the loosest electron from the atom. The lower the ionization energy, the more easily an element loses electrons. And just like with metallic character, two factors contribute to ionization energy. First, metals want to lose electrons, which means that they and they do want to lose the electrons because that gives them a more stable electron configuration, and this means they have a lower ionization energy than nonmetals. So if we look here at lithium, this shows what the ionization reaction would look like. So we have lithium going to lithium plus, so lithium ion, and losing one electron. The energy it takes to do that is 520 kilojoules per mole. For fluorine to lose an electron and become an F plus ion, it would take 1,681 kilojoules per mole, so a lot more energy. And in fact, fluorine really doesn't want to form an F plus minus ion. It would rather charge an F minus ion. So it has a very high ionization energy. And so the electron configuration, like whether the element gets a favorable electron configuration by losing electrons, is one consideration. And then the other is, again, the size of the atom. So if the electrons are close into the nucleus, they're harder to lose. And so that means basically the ionization energy increases. And if they're further from the nucleus, it's easier for the electrons to be lost, and the ionization energy decreases. So let's look at what this means in terms of trends on the periodic table. First, we'll look at going down the table. From the top to the bottom, ionization energy decreases because electrons are further from the positively charged nucleus, and they're easier to remove. So ionization energy is related to metallic character, but it's the opposite trend, because remember, lower ionization energy is basically a bigger metallic character, or more metallic character. So ionization energy decreases from top to bottom. Now from right to left, ionization energy increases, because losing an electron is less likely to result in a stable electron configuration, and because, again, the atomic size decreases across the table. The electrons are closer to the nucleus and harder to remove. All right, and so the final periodic trend we're going to look at is electronegativity, which is the relative ability of an element to attract electrons. So electronegativity is a measure of how non-metallic an element is, whereas metallic character and ionization energy are both measures of how metallic elements are. So as with the metallic character and ionization energy, two factors contribute to electronegativity. The first is how much the element wants to gain electrons, and nonmetals do want to gain electrons a lot, whereas metals don't want to gain electrons at all. So for this reason, nonmetals have a higher electronegativity. So let's look again at lithium and fluorine. Lithium has and electronegativity is relative, so it's like comparing one element to another. And so lithium has a electronegativity of 1, and fluorine has an electronegativity of 4, so it's more electronegative. So the other thing that contributes to electronegativity, just as with ionization energy and metallic character, is how close or how large the atom is. So notice in this one, we're trying to gain electrons that aren't associated with the shell. They're outside the shell, so these are ones that are maybe from another atom. And they want to be, so the atom is going to be gaining this electron. Now, if the electron shell, the valence shell, is a small shell close to the nucleus, that negatively charged electron can get close to the nucleus. It feels a stronger attraction, and is more likely to be basically grabbed onto by the nucleus and incorporated into the atom than if we have a larger valence shell that's further away. So what does this mean in for terms of trends? If we look at going down the table from top to bottom, the electronegativity decreases because the electron can't quite get as close to the positively charged nucleus. It doesn't feel that strong pull, so it's less electronegative. From left to right, electronegativity increases because gaining electrons is more likely to result in a stable electron configuration. Remember, nonmetals on the right side want to gain electrons, metals don't. And also the electrons, the atom gets smaller so that the electrons can approach closer to the nucleus. Okay, so now we're going to summarize the trends in electronegativity. Atomic size is simply the diameter of the atom, which depends on the diameter of the electron shell. Remember, the nucleus is really, really tiny and takes up hardly any space at all, so the atom is mostly the electron shell. Going across the table, atomic size decreases because the electrons within the valence shell are all in the same valence shell, so they're not really further out, and the valence shell actually gets pulled into the closer to the nucleus because the charge of the nucleus increases going across the table, which pulls the negatively charged electrons in. Going down the table, atomic size increases because the electrons occupy larger and larger valence shells, and each one is further out from the last, so that results in a larger diameter. Now, metallic character, or the ability to lose electrons, is when we're talking about a higher number, we mean that what that means is that the substance or the element is more metallic. Now, as we go across the table, metallic character decreases for two reasons. First of all, the elements are less likely to achieve a stable electron configuration, a noble gas configuration, by losing electrons. So on the left side of the periodic table, it's easy to lose one or two electrons and achieve a more stable configuration. For the nonmetals, this would be very hard to do because they'd have to lose a lot of electrons. And across the table, metallic character also decreases because the electrons are pulled closer into the nucleus and feel a stronger pull from the positively charged nucleus. Now, going down the table, metallic character tends to increase because the electrons are further from the nucleus, the valence electrons. They're in a further out shell, and it's easier for them to be stripped away from the nucleus. Now, electronegativity is kind of the opposite of metallic character. It's the ability of electrons or elements to attract electrons. And a higher electronegativity means more non-metallic, more easily, it means that the element is more easily able to gain electrons. Going across the table, electronegativity increases for two reasons. First of all, elements are more likely to achieve a noble gas configuration by increasing electrons at the right side than at the left side of the table. And also, the shells are smaller so that an electron that's approaching the valence shell can get closer to the positively charged nucleus where it feels that positive charge and gets basically sucked in. Going down the table, electronegativity decreases because the electron shells valence shell is larger and larger, and the electrons can't get quite as close where they feel that positive charge and get pulled in. ionization energy, when we have a higher number, it means more non-metallic or less metallic. So that's the energy required to lose an electron. And going across the table, ionization energy increases. And again, this is for two reasons. First of all, because of the electron configuration, or what happens when an atom loses electrons. So going across the table from left to right, electrons are less likely to achieve a stable configuration by losing electrons, so it takes more energy. And also the electrons are pulled in close to the nucleus, so that there's a stronger pull, and that also makes it harder to lose electrons. Going down the table, ionization energy decreases because the electrons are further and further, the valence electrons are further away, and it's easier for them to be lost because they don't feel the pull of the positively charged nucleus as much. And that is it for periodic trends.